When we begin to study the dynamics or how things change in a complex system, it seems less obvious on the surface than our earlier models with a single spring mass, for example. So what we're going to do is go back to basics. To start off with, let's imagine our building system here, a two-story building. And what are the physics involved with this? Well, if we imagine the ground is fixed, then if there's a vibration in the building, it means there's a slight bend in this beam. Now, I've looked at beam distortions. That's helpful, but not necessarily the most easy way to focus on this particular question. If you look at a beam like this, though, and as it distorts, it's going to resist that and want to push backwards. And so what that boils down to is that these vertical members are equal to springs. And when are they happiest? When they're perfectly vertical. So if there's a deviation of the floor to the left or to the right, then this is going to resist that motion, exactly like a spring, and push it back. And if we imagine this then in a horizontal context, if we talk about the position of the floor, so this floor has some mass to it, it's going to have some natural position, let's call it x naught, let's call it x1 naught, because there's going to be two floors running around. So there's some natural position, and as it moves left or right, a spring resists it. Just like this floor here has a natural position, and if it moves left or right, the spring, which are these support beams, will resist it. The other interesting issue is that there are two floors here, so we actually have two different masses to worry about. And the spring force applies the same way on this, except with a little variation. If both of these masses were moved over at the same time, this beam would be happy. That'll come out in the physics a little bit. But at the end of the day, we've got floor 1 and floor 2 joined with these vertical members, which we've said are like springs. And so it would be like having this second mass attached not to the wall, but back to the first mass with some new spring, and it would have some equilibrium position itself. When we go to look at the physics of this, it's important to note that if both of these were moved the same amount, say to the right, the spring stretch that results would be none. If they're at equilibrium now and we stretch both of these masses out, this spring will still be in equilibrium. This one would be stretched out. Absolutely. But the stretch in the second spring is relative to the displacement of these two with respect to one another, not in absolute terms. And we'll see that play out when we look at the free body diagrams and the physics and the forces. So to answer this question here, specifically, if x1 and x2 are increased by an equal amount, then we get 0 in the second spring, 0 force in the second spring. Moving forward, we're going to use that spring system as our model. We know it maps back onto the building, but it's easier to visualize and understand the spring system for most people. So if we draw our mass 1, notice it's attached to exactly two things in the horizontal direction. That's all we care about. And what that means is the force calculations are going to be straightforward. We're going to have a spring force 1 and a spring force 2 acting on mass 1. And what that means is the mass times the first position's x1's second derivative is going to be F spring 1 plus F spring 2. And that spring 1, we've seen this before, because it's attached to a wall here at the other end, we're going to have simply negative k x1. The more this thing moves out, the larger the spring force is because it's away from equilibrium relative to the wall. The other one's a little trickier. So if we have the second mass here, it's not part of our free body diagram, but it's relevant to this force calculation. What we care about is the distance between m1 and m2. So there's an m1, or an x1 rather, minus an x2 in there. And there's going to be a k. And the question is, does this make sense? All right, well, let's imagine in isolation those two masses relative to one another, and we're interested in this force applied to mass 1. Well, if I increase mass 1 position, so if I increase x1, what happens to the spring? It's going to push itself back. The resulting spring force would be negative if we keep this one constant. Well, if we increase x1 here, we're going to get a negative force overall, so the second spring would be pushing backwards and resisting this forward motion for m1. As another check, if we increased m2 and kept this mass fixed, so we hold this and stretch out this mass, which direction would m1 want to go in? Well, it would want to go in the positive direction, because it's going to want to follow mass 2. It's going to have a stretch spring, it's going to pull it to the right. The upshot is, if m2 is positive and m1 was 0, we should get a positive force. Well, if x2 is positive, then if you look at this calculation here, it leads to the second spring force also being positive. So we get a model that actually looks like a spring force, except it's got a more complicated term because of the fact that this spring is stretched relative to two moving masses rather than one fixed wall and one mass. On the plus side, if we start looking at m2, we can leverage some of what we just did. This only has one force acting on it, so mx2 double prime is simply going to be the force on spring 2. And how does that play out? Well, it's going to be the equal and opposite version of this. All the study we did in this little diagram here was how would that spring affect mass 1? If we just repeat the calculations but have it act on mass 2, we're going to get the equal and opposite reaction, which is k x1 minus x2, no negative, so explicitly a positive here, versus the negative k in this one here. So now we've analyzed this more complicated physical scenario, and we ended up with, surprise, surprise, two differential equations. But notice there's two variables unknown, and those are x1 and x2. And it makes sense because we want to predict the motion of both masses over time, which can move not independently, but they have their own trajectories that are separate from one another, distinct from one another. So it makes sense that we should have to solve for them separately as well. If we write out the entire set of forces that we found before, we would have had this for the first term, and our second derivative mass acceleration would have been the positive k x1 minus x2, or you could swap these and make that negative. There's other variations you'll see in textbooks, but these are the fundamental equations. And we'll also slide in a quick note here that we're assuming that the spring constants are the same. That just makes life a little tidier, but this could be one constant and this could be k1, k2 for the two different springs if we wanted. If these are the same, we can actually group some terms here and get that first term to have negative 2k x1 and plus x2. And this is a nice point to make. You see some of the sign changes or the sign structure in this. When we're talking about the first variable, we end up with negative terms with respect to it. We know that if we stretch the first mass out, it gets pushed back. The second mass has the opposite effect. When we push it out, it drags the first mass with it. And we get the same response on this term here, if we call this correctly x2 on the bottom. And so those two equations make up a system of differential equations. And these in particular are second order differential equations because we have the second derivatives here. So this is new, and we have to figure out some way we're going to approach this to be able to solve it. We'll see one strategy for that in the upcoming videos.